And it looks like we can start. Welcome back, everyone. Feels like it's been quite a while since we've done statistics, thanks to the exam one that we got through, and then the President's Day holiday that we didn't meet on Monday of this week. But the course will get back into its normal flow pretty shortly. We will possibly finish chapter 14 rather, today. And then we'll be moving into chapter 15, just more topics on both the confidence intervals that we worked on in chapter 14 and also the hypothesis test that we're about to start in chapter 14. But before we jump in, looking into hypothesis testing again, any questions or comments at the moment? Okay, well, let's begin, folks. Welcome back, everyone. So pretty much a lot of our chapters are going to be split in two. Half the topics in a chapter will possibly be about confidence intervals. The other half of the topics might be about hypothesis testing. And chapter 14 was, again, mainly an introduction to both topics at once. So it's a little bit longer, but if it's a brand new subject, since this class doesn't have statistics as a prerequisite, then taking the extra time to talk about these details is well worth it. So here's where we left off. A lot of stuff. So let's go through this kind of carefully. We are defining a null hypothesis, which is a statement or a claim of no change in the population, and an alternative hypothesis that has three different kinds of forms, which is the competing claim, the claim that the researcher is usually trying to find evidence in favor of. So once we carefully state what a null hypothesis is, and one of the three alternative hypotheses, we'll collect data, calculate a p-value, which is just a probability, and make a determination whether we're going to reject the null or fail to reject the null. Those are going to be our only two possible conclusions. The biggest hurdle, though, getting through hypothesis testing is just stating those hypotheses. You have to first say, what is your parameter? In this problem, the parameter was p because we had categorical data. It could be mu if it was quantitative data, or there could be several parameters at once, maybe two or more means, two or more population proportions, and so on. Then the null hypothesis for these data, it was a statement of seatbelt compliance was 65% in 2008. And that's our statement of no change, that in 2026, we have the same amount of seatbelt compliance in Massachusetts as we did about almost 20 years ago, 2008. But this problem says the state wants to know if that has changed, and that's what we're seeking evidence for, a change in the population. So the null is a statement of no change whatsoever. We just took the value from historical data and said that population proportion P is 0.65. When the state wants to know if it has changed, we formed the two-tailed alternative hypothesis. The parameter P is not equal to the 0.65. Then, if we had the raw data, we could start calculating p-values, make a decision if we're going to reject the null in favor of the alternative or fail to do so. So, other thing that's tricky about all this is the type and form of your hypothesis depends on your data in the very first place, whether it's quantitative or categorical. And so we're going to look into a part B of example 5, going back to quantitative data. But we'll be returning to the categorical case later on. I believe that's going to be chapter 19. We'll be handling categorical data. But any questions at all, folks, with the refresher on this problem? Okay, this one went kind of fast because this is the whole context, just 2 sentences. But for a more realistic problem, there's usually a lot of stuff we have to filter through. And so that's what's going on in part B. So we've looked at this data before, so it's kind of interesting to see it come back again. This was, I believe, the first problem of the course, this context. We're told that ankle brachial index, we'll just abbreviate that to ABI, compares blood pressure of a patient's arm to the blood pressure of a patient's leg. We're also told that the ABI can be an indicator of different diseases, including a slew of arterial diseases and otherwise. And a healthy ABI is at 0.9 or higher. Let's highlight that just to come back to it if we need to. Now, the context of the data really gets going when we look into the study that was performed by these authors. They said the researchers obtained the ABI of 187 women with peripheral arterial disease. So that's our sample size in this problem, n equals 187. We had a result of a mean ABI of 0.64, but that's not the parameter, that's the statistic. So let's carefully write that in as X bar is 0.64. There's also a standard deviation of 0.15. This is referring to the sample standard deviation, so we can also write in S equals 0.15, coming from this part right here. And I believe we left this wording in when we looked at this problem for the first time, but now we're going to be able to say something about this. Significance level at 1% is going to be a threshold from which we'll reject a null hypothesis or fail to reject it. It's a level of evidence that we need before we go ahead and reject a null hypothesis. So when you see anything along the lines of significance level, we write it in this way. This is a quantity alpha equals 0.01. Coming from this part of the context. So lots going on with this already. We've indicated 4 different values. The question of the problem is, do the data provide significant statistical evidence to conclude that, on average, women with peripheral arterial disease have an unhealthy ABI? So this is the entire research question. Let's highlight this so we can come back to it. And from all this wording so far, we're able to recast the research question in terms of a null versus an alternative. But this time the parameter is not P. If you see a sample mean, sample standard deviation, you're dealing with quantitative data. So let's write that into the problem. The data is quantitative. And this implies the parameter is mu, the population's mean. So we're about ready to get started. Any questions, folks? Just diving through that context and finding those values. Okay, before we dive into the hypotheses, really the best advice I can give is look before you leap. We don't want to start writing things down unless we know exactly what is mu. And so that's what this part of the instructions on example 5 is all about. It says, define the unknown parameter in terms of the context. And we did that on our very first day of the course. This was an exam 1 question as well. There are really 2 unknown parameters, but we're only testing 1. So when it says the unknown parameter, it's implying mu is what we need to define. And we'll state hypotheses with a mu put here and a mu placed here as well. So let's begin by writing down exactly what mu is going to be. Mu is going to be equal to the population mean, or you could say average here if you'd like, ABI, or, well, the sample had 187 with peripheral arterial disease. The sample came from the population. So that implies our population is, for all women with peripheral arterial disease. Again, that's probably almost close to verbatim what we did on the very first day of the course when we looked at this context before. But now we can go a little bit further. If we really want to analyze these data and find out if there's evidence, significant statistical evidence, that women with this condition have an unhealthy ABI, we can now do the next step of stating the hypotheses. So we're getting there to analyzing these data in full. Any questions with this hard step right here, just writing down the parameter? Okay, next step, let's write it out the structure and then we'll fill in the values. Test a null hypothesis, H naught, that mu, equals, and we'll plug in a value here in a moment, against, or you could say versus, and alternative hypothesis, HA. For mu, we don't want to put necessarily anything in here just yet until we look at the research question really, really carefully. So there's two missing things still that we have to find in order to state this alternative hypothesis. Notice that they are asking the question that do we have evidence to conclude that on average, women with peripheral arterial disease have an unhealthy ABI? We can wrap that back to the statement that a healthy ABI is 0.9 or greater, so we have a direction. The last problem was asking for if the value has changed, but there's a specific direction this time. If we're testing for unhealthy and healthy is 0.9 or higher, this is going to be a less than for a left tailed test. So the language of the actual research question implies that specific direction. So we'll put less than here. It'll be less than this value, 0.9. That's going to be the hypothesized value, the value that we're going to test. So this one, we often write down as a mu naught, and it will be equal to 0.9. So once we have that new value, we plug it in here, 0.9. In our alternative, we'll have less than 0.9. We're still not 100% complete. We want to say what level of evidence we want on this test. So let's say here also, we're testing at alpha equals 0.01. That came from the level of significance being set at 1%. So this is how our textbook would set up these hypotheses. Notice if you're taking, for example, the biometry lab, it might be set up a little bit differently, and that might look a little bit funny to you. But any questions at the moment? Okay, because our textbook teaches how to set up the null hypothesis differently than the biometry lab, and about half of the people in this class are also taking biometry, it puts us in a kind of a weird conflict. I'm usually going to go the way our author does it so that if you're reading the textbook, you won't feel like I'm suddenly doing something differently in class. But I'm not too picky on how the null hypothesis is set up. As long as you have an equality in some form, you're all set. So let's say just here, a second version that's acceptable for the null hypothesis would be H naught mu. If we have less than here, we flip the direction and include an equality. Mu greater than or equal to 0.9. So if you prefer to write it that way, no harm done. That's a very sensible way to go because we want to negate this statement in the null hypothesis. They should be negations of each other, and that's the right negation. Our author kind of simplifies. He will only put equality on the null hypothesis no matter what, which is kind of confusing in a certain sense. But we have it, folks. This is the full statement of hypotheses. We had to say exactly what the parameter mu is, what the value to be tested against is 0.9, and the direction of the test. It being a left tail test means this time it can't be non-equals. It has to be specifically less than. What would we do next? We would have to calculate a test statistic. We'll define that shortly. Once we have a test statistic, we'll compute a p-value. We'll do that next. And if our p-value is small enough, smaller than a 0.1, we're ready to make the conclusion in favor of the alternative hypothesis by rejecting the null. So those are going to be the next steps we're going to look into for the next part of the notes. But this is the big hurdle, just saying what the parameter is and forming the tests. Any questions at all, folks, getting through those steps there? Okay, once we get here, pretty much hypothesis testing is kind of like a set of mathematical equations that you plug in, a probability that you compute. You'd be using the p-norm function. So RStudio makes a comeback. P-norm will be pretty helpful here. And you just check if your p-value is smaller than this. So we're going to explain all those bits of logic that piece by piece as we go. And if this chapter 14 feels like it's quite a lot, the good news is we're going to revisit both confidence intervals and hypothesis testing in chapter 17, 18, 19, 20, and so on. So we keep reinforcing how all this works in every new situation. So here's the next level of dealing with the hypothesis test. Here we finally have our entire full procedure. The hypothesis test for a mean of a normal distribution says the first thing we want to do is gather a simple random sample, we'll denote it by n. From a normally distributed population, it doesn't have to be normally distributed, but that's going back to our simple conditions for inference. We'll make this a better procedure in chapter 17, like we mentioned. So we'll come sample from the normal distribution with an unknown mean mu, which makes sense because that's what we're testing this time, and a known standard deviation sigma to go along with what we were doing on condition 3 here. First thing we'll do is determine the significance level alpha for the test. And the typical values are 0.10, that'd be a low level of evidence before you reject the null. The last problem was at a 1% significance level of 0.01. And these are probably going to remind you of, say, a 90% confidence level goes along with a 0.1 significance level. 99% confidence interval goes along with a 1% significance level. Next thing we calculate is the test statistic. We take the sample mean minus the hypothesized value, that's this part right here when we set up our hypotheses, divide by sigma over the square root of n. The reason we're doing that is we know that the sample mean x bar is distributed normally with true mean mu, and standard deviation sigma divided by square root of n. And this is the major content of the central limit theorem. So we know sigma, so we can divide by a known value. We don't actually know mu, that's the unknown in the problem. But returning to the logic of the hypothesis test, the very first thing you do in hypothesis testing is you assume the null hypothesis is true, that it's the reality of the population, and just see what happens under that assumption. So this is assumed true. The very first massive step of hypothesis testing. But if you assume that's true, you have a value here as well. You'll know the sample, you've cranked it out from your sample data. You know mu naught, it comes directly out of the null hypothesis. And so you can calculate z. Often this is called a z-score. But aside from its name, the most important thing about z is what it does. This measures the number of standard deviations, because we're dividing by the standard deviations, that x bar, your actual sample data, is away from the claim the mean is mu naught. So if this claim is ridiculous, if it's really false, then this will be a large value. It'll be a whole bunch of standard deviations, maybe 5 or something along those lines, maybe even higher. But if this is close to a true statement and our sample is low or even at a high sample, if this is a very close to true, then it would be really unlikely for this to be large. This is probably going to be a small amount of standard deviations, maybe less than 1, in which case our p-value will be large and we will fail to reject the null hypothesis. So this is the next hurdle of the logic so far. We take our data, we take our claim from the null hypothesis, crank out a number of standard deviations. After we have that number of standard deviations, we're going to compute a so-called p-value. The p-value is going to be the probability of attaining the sample mean x bar as extreme as what we obtained, or more extreme, under the assumption the null hypothesis is the literal truth of the population. So if our p-value is small, we'll reject the null hypothesis, and if it's large, we'll fail to reject. But that was a lot of words so far. Any questions at the moment? Okay, well, good news here is our z-score is going to be distributed normally. So it'll follow the z probability distribution, distributed normally with a mean 0, standard deviation 1, so the standard normal curve. The tough thing about hypothesis testing is recall that there are three alternative hypotheses, which means the way we compute the actual p-value depends on which test it is, right tail versus left tail versus two tail. But the good news is this is a great table to come back to, and it's not anything we've done differently. This is just redoing a normal probability distribution computation. So let's write down what these are going to look like in each one of these tests, what the syntax will be, and then we'll do our first hypothesis test. So first we're assuming we're doing a right-tailed test. Right-tailed means we have a greater than direction right here. If that's the case, when we calculate our z-score, it can be anywhere on this curve, but the key fact that we'll use is we'll shade to the right. So one reason it's called a right-tailed test is because we're actually grabbing the p-value as an ordinary probability, like we've all done in chapter 11, from the right tail of the normal distribution. So supposing our test statistic z was somewhere here. Again, it could be anywhere on this curve, but for the sake of one drawing, if I put z here and shade to the right, that area itself represents the p-value. So the p-value is here. And how would you calculate it? It's just ordinary in our syntax, p-norm z. That's actually all you have to put in. You don't have to specify the mean or standard deviation because 0 and 1 is the default. It's already been standardized to have a mean 0, standard deviation 1. So that's it. That's the whole p-value, but only for a right-tailed test. I'm noticing I made a mistake there. One small correction. Anyone see what the issue is if we leave it just like that? There's got to be one additional statement. The issue is, sorry, go ahead. Yeah, exactly. If we're shading to the right, but we don't specify lower dot tail equals false, our student is actually going to grab the area to the left and we're going to get a funny value. So in this case, we have to say lower dot tail equals false. Now that's it. That's the true syntax for getting that p-value. And if we go to a left tail test, all we're doing is shading to the left. So not too bad of a change in logic there. So here, shade to the left. Now this test statistic z will have kind of a small p-value, actually possibly still sort of large. Our p-values get a little bit more smaller once we're beyond 2 standard deviations. But to just emphasize z can be anywhere, let's put it here. Here's z. Because it's a left-tail test, I put it towards the left, but it could come out positive. Anything could happen. But the important thing with the left-tail test is now we're shading to the left. And this time the p-value is p-norm z. And this time that's really what it is. We're going to default shade to the left if we don't put anything like lower dot tail equals false. And this has the mean 0, standard deviation 1 coming from that probability model already built in. So that's pretty nice syntax, even faster than the right tail test. The tricky one is the two tail test. And what makes it tricky is it's also the default test. This is the one that you would default to unless there's specific wording from the context of the problem that says you're doing either a right or left tail test. So if you see this, we're shading to the left and right. We're using both tails. So that's kind of interesting. If your test statistic z was positive, say it would end up there for a positive z, you would shade to the right of that value. Then you would negate this sign. So whatever this is, looks like a 1.75, go to a negative 1.75. Here is negative z. You also shade to the left of negative z. So we have two regions we have to aggregate together to get the p-value. And already this tells us one important fact about the two-tailed test. the p-value of the two-tailed test is always twice as big as the p-value would have been on a left tail and a right tail test. Well, the way we get this is it's going to be twice the area under the z-curve to the right of the absolute value of z. We're saying absolute value of z because my picture can change based on z being positive or negative. So we take away that change by just saying absolute value. And this is the way our author does it. He goes to the right of the absolute value of z. That means he's taking this area and doubling it. That makes sense because the normal curve is 100% symmetric across its mean, 0 in this case. So if you want this area and this area, it's okay to just double say this one. This is our author's approach. So using that definition, we would say the p-value is going to be equal to p-norm. ABS gives you absolute value, z, and lower dot tail set false. So that would be the p-value in that situation. So now we have the test statistic, now we have the p-value. If we were doing a statistical problem and we just finally got the p-value, the next thing we have to do is make a decision. Are we going to reject the null or fail to reject the null? It'll be based on the size of the p-value. What we want, if we're trying to show the alternative is true, our actual research question, we're hoping for very small p-values. The moment it's large, we don't have statistical significance. But any questions at the moment, folks, getting through this chart here? Okay, so now that we have the p-value, here is the next big and important table. Remember that significance level alpha that we kept bringing up over and over again? It makes a comeback right here. I'm not sure what I was doing. I thought I was trying to shade it. Here we go. The significance level alpha is what we compare the p-value against. There are only two possible conclusions in hypothesis testing. We can never make an assertion that the null hypothesis is true. We're going to say, in the good case, a small p-value, smaller than our benchmark for evidence, the significance level alpha, we'll say we reject H naught, and we have significant statistical evidence that HA is true. We have to say exactly what that means using the context, but if you've already said what the parameter is and what the alternative hypothesis is, that's usually not the hard step. And this is the bad case. And notice the equality that's built in there. My significance level alpha is, say, 5%, 0.05, and if by some mathematical miracle the p-value is exactly 0.05, even there, we fail to reject the null hypothesis. But the actual conclusion we write, it's kind of sad in its wording. It says, the study has failed to find significant statistical evidence that the alternative hypothesis HA is true. So those are the only two conclusions. And another reminder, we can never accept the null hypothesis as true. If we did, that would be 100% circular logic, because recall, our whole method starts by assuming it's true. We can't assume it's true, get a large p-value and say, aha, we've proved it's true. We've gone in a literal circle with our logic if we ever did that. And in fact, this is the same analogy in the court of law. In the court of law, the null hypothesis is that the defendant is not guilty. The alternative hypothesis is that the defendant is guilty, but the prosecuting attorney fails to show guilt. The conclusion is not that the defendant is innocent. The conclusion is we fail to show that the defendant is guilty, and then we just let him go. There's no proving innocence whatsoever in a court of law. And same exact logic and analogy tells us hypothesis testing will never have the conclusion that the null hypothesis is true. So we have to stay very far away from that when we write our conclusions. So notice how close these statements are. You either found significant statistical evidence or you have failed to find significant statistical evidence, both talking about the same hypothesis, the alternative one. Well, with all this knowledge, we're ready to do a top to bottom statistical hypothesis test. And then we'll do some concept questions more about p-values right after. But any questions at all, folks, with this kind of big adventure in logic getting down to here? Okay, my next problem is a pretty convoluted looking scenario, but it's a fun one to get through on a very first top to bottom statistical analysis. There's a lot of context, but this is par for the course for a real statistical problem. You might have pages of context if you're dealing with something that's a really serious statistical problem needing to be solved. It starts off by saying the Board of Health of a particular state, say Idaho, was called to investigate claims that raw pollutants were being released into a river flowing past a small residential community. So this could trigger all sorts of legal trouble for the company. The next part of the drama says, by applying financial pressure, probably fines, the state was able to get the violating company to make major concessions towards the installation of a new water purification system. So that's that whole sentence. So there's concerns of raw pollutants being dumped. The state kind of twisted their arm for this company and made them change their systems, some kind of new water purification. But it looks like this is going to take a while to install. It says in the interim, or otherwise you could say, meanwhile, while they're working on getting this new water purification system going, in the interim, different production systems were to be initiated to help reduce the pollution level of water entering the river. So a lot going on already. We have a polluting company. They're agreeing to do a water purification system, but before it's even installed, meanwhile, in the interim, they're just going to reduce the pollution level of the water entering the river, which probably means scaling back their production, taking a hit on their revenue, all that kind of nasty stuff for the company. There's kind of a balance between helping the people in the community and not hurting the company too much all at the same time. But you know how companies are. They don't want to necessarily dip into their revenue, give up profit if they don't have to. So the state is going to monitor this company. So this is the next level of the drama, to monitor the effect of the interim system, where they're just reducing the pollution level of the water. They took a random sample of 50 water specimens. So now we have a sample size. Let's pen that in. It measured the dissolved oxygen count of the water in parts per million. I think it's an interesting question to ask, why are they measuring the dissolved oxygen count? And there's a very good reason for that. In many cases, if you're dropping raw pollutants into water, there's plenty of bacteria, other organisms that are going to feed on that. Their process for feeding on the pollutants are aerobic reactions, so that's going to pull oxygen out of the water. And if there's enough pollution and the bacteria kind of explode trying to feed on this stuff, they can actually drop the oxygen level of the water substantially so that it kills a bunch of organisms. A whole bunch of crazy things can happen for dumping raw pollutants. So that's why they're looking into this specific thing. How much oxygen is actually in this water? If they find it's low, that will be evidence of the company is still in violation. They didn't actually reduce the pollution level. So lots going on in the problem so far. Any questions or comments at the moment? Okay, so they're measuring dissolved oxygen count, parts per million. It was taken throughout the month at a location downstream from the plant. We're told that the sample mean of 5 parts per million was obtained. So that's the dissolved oxygen count for the 50 water specimens. We hope that this was a good sampling design, because if they didn't do this properly with some kind of random sampling idea, the company will be able to complain and say, your statistics are invalid. We were actually doing the right thing, but you didn't even use a random sample. So it's critical that they do this right. This is a hard problem in and of itself, getting a random sample. But let's assume they did it all correctly, and X bar comes out as 5.0 parts per million dissolved oxygen count. I'll just call it 5.0. We're also going to make another assumption Assume the population standard deviation of the dissolved oxygen count in the water is 0.70 parts per million. Now, I'm not sure where they would have gotten this. They're probably going to have to use some biologists, some people who are familiar with this kind of stuff, some geosciences to tell us that's a reasonable value. And if they mess that estimate up again, the company can say they were doing everything right, but you gave a very poor estimate for sigma, the parameter value, 0.70 parts per million. So even though it's a fake problem, you can imagine if this is a real situation, this is high stakes. If the state messes this up, they're going to be sued by this company and probably lose. Well, here's the entire research question. Is there evidence that the mean dissolved oxygen count in the water is less than 5.2? What's 5.2? It's the mean reading of this location over the previous year. That's the entire research question, so it's basically the alternative hypothesis written out verbally. So let's highlight this. It also gave us a very specific value. That 5.2 right there, that's going to be the value that we're going to be testing against in the null and alternative hypothesis. So the hypothesized value in the formulas, it's written as mu naught. And this problem is 5.2 parts per million. And it might not look very good so far, right? Because the sample mean came out less, but if we just made a conclusion based on the sample mean, we're going to probably be sued if we're working for the state by this company, because the mean is not the whole story, the mean of the sample. The variation, the variance, or standard deviation, variability, is also part of the story. So we can't make any conclusion just based off the statistic. We have to go further than that. And this is going to be our benchmark for evidence, a significance level of 0.05. So that statement gives us alpha equals 0.05, or 5%, you could say, in the problem. So this is the entire top to bottom analysis of just the context. Now we're going to actually analyze this data in full. Well, any questions so far, folks? Just digesting this material. This is a lot for just one problem so far. Okay. Again, when you're seeing a problem like this, whether you're looking at ankle brachial indexes like in the last problems, or this kind of context, it's good to read these a couple times. Read it once to get a feel for the problem. Read it again to try to extract these critical values like n, x bar, sigma, mu naught, and alpha. Then once you finish the entire problem, I'd recommend read it again just to make sure you didn't miss anything, that your conclusions make sense, that there wasn't any part of the problem left unaddressed. Well, we're looking at our complete analysis structure. We're doing this with a hypothesis test. The first thing I'll ask you to do for this problem is just say what the practical question is. You can either directly cite it into the document or in your work, like we mentioned before with confidence intervals, or you can put it in your own words. If I was to put this in my own words, I would say the practical question is there significant statistical evidence this company, how they say that this was, yeah, they called it a company, so I'll call this company has not reduced the pollution. And we know they eventually will. They're going to install a water purification system, but recall, this question is really about in the interim, before they installed the purification system, they agreed to reduce the pollution level of the water. So that's the whole question. Do we have evidence that they didn't do it? We're going to go and see if we have evidence against them to put even more financial pressure on the company. We're imagining we work for the state as a statistician. Once we have that down, we need to say exactly how we're going to answer this question when we make our conclusion. But that's done by, just doing this last problem that we started with. We're going to state the actual unknown parameter. It's not mu naught, that's the value we're testing against. Then once we have the parameter, we'll state the null and alternative hypothesis. So once again, it just returns to the very first question we did of the semester. These are kind of tough questions. That's why we took a preview of it. We've been thinking about it all semester long. And now we're back to here. I'm writing it in as mu because the data is quantitative. We have a sample mean. That's enough to tell us use mu. You can say that this is the average of all, implying a population, or we could just say it's a population average of something. Or sometimes you could say it's a true average to emphasize this is the real value of the population. Or you could say it's the true mean. There's lots and lots of different ways to say it. This time I'll go with true mean. But you have to say exactly what it is using the context. So we'll say the true mean, well, it is an average. An X bar has estimated mu. So we can say what the unit is just based on what we wrote. It's part per million dissolved oxygen count. So we'll say true mean dissolved oxygen count. And this was taken downstream from the plant. And just deciding how to include this. It's specifically in this time, in the interim, when they're using different production systems to help reduce the pollution level. I'll just abbreviate that in the interim, borrowing the language you already see in the problem. Let's highlight that just so we can reflect on that as we write this down. So dissolved oxygen count downstream from the plant in the interim. The time between when they have the new purification system, the time where they are agreeing to reduce the pollution level. So this is the superstar of the problem. Our conclusions are going to come right back to mu. The next thing we'll say is exactly what the null and our alternative hypotheses are going to be in this problem. We will test H naught, mu, and then we'll put something there against HA, mu, and we'll put something else there as well at the significance level. I'll just write in alpha equals 0.05. So the moment our p-value drops below that figure, we have evidence that whatever this statement is going to be is true. Let me just kind of space this a little bit better. The next part we can put down is both the null and the alternative hypothesis are going to depend on this value right here, the hypothesized value, 5.2. Here we write in it's directly equal to 5.2. And here, 5.2 will go somewhere. Let's put it to the right. But we have to decide now, is this a left-tail test, a right-tail test, or a two-tail test? Well, if this is the alternative hypothesis, it should give us a direction. And if it doesn't, the default is two-tail test. We're being asked, let's look at this again. Is there evidence that dissolved oxygen count is less than 5.2? And that's exactly what we need. This tells us this is a left tail test. So less than for left tailed test. That means we'll put a less than here. And it means here you have options like we mentioned before. You can also put greater than or equals as well. Well, this is so far over the hump in hypothesis testing. We have to do really careful work to get everything out of the context. Reflect on what are we even trying to do? That's the state phase of the complete analysis. Then we have to say exactly what our parameter is in terms of the context so we can define both the null and alternative hypothesis as precisely as possible. From here on out, it's not so bad. It's like a math problem now. But any questions so far, folks, to get to this stage? Okay, what we're going to do next is some condition checking. And this is kind of weird in this section because what conditions are we checking? three things: that we have a random sample, the variable has a perfect normal distribution, and we know the population standard deviation sigma. We don't have to state condition 3 because this problem doesn't work unless that's in action in the problem itself. But you know what's tough about this problem is, how do we check if this is a decent statement based on our data? In our confidence interval problem, this is what we did. We took all of our data. This was the radioactive Pacific bluefin tuna. We stuck it into a histogram and decided, is it plausible in a sample size of, I think this was 16 or 18, that we could get data like this from a normal distribution? It wasn't heavily skewed. There wasn't bad outliers. So we said, yeah, it's plausible our data could look like that. But this time in our problem, the situation is different. All we know is that we have 50 observations and the mean of the sample is 5 parts per million. We can't put that in a histogram, but you won't know we still have the central limit theorem. So let's bring in the central limit theorem for us. Just park this somewhere. First, we better get to it. There it is. The central limit theorem is going to tell us, even if the condition on normality is in fact not true, if this is a little bit weak, if the population is slightly skewed, in fact, that's okay, because if the values of n are large enough, we still get an approximate normal distribution or the sampling distribution of the statistic, x bar. Our sample size is actually quite large. It'd be pretty unusual to find a population where sample size 50 doesn't work. In the central limit theorem problem, I had to work pretty hard to show what those examples would look like. So we can actually get through that condition just citing the sample size. We were told we had a random sample. We're not sure on the sampling design. That's probably a lot of information there. When we go through the conditions, we can now start checking them off. Condition 1, we have a random sample as required. We prefer that this is a simple random sample, but any level of randomization helps with getting through this condition. Next, condition 2. Well, did it tell us anything about the normal distribution? Doesn't look like it. I don't think anything here saying assume that these water samples are distributed normally. That'd be quite a statement, right? But we can say, since the sample size n is 50, the central limit theorem is effective even if the population is not perfectly normally distributed. So we're actually on good shape with this one. And that's pretty much all we really have to say for the conditions. Condition 3 says we don't know the mean of the population, but that's why we're doing a hypothesis test. The value of mu is a complete unknown. We do know the population standard deviation sigma. That's just a requirement for our procedure to work. So it doesn't hurt if you did want to mention 3, but that's a good one to skip, I'd say, for these kind of problems. So we can say here, overall, the conditions are met. And now we're ready to calculate the test statistic and then the p-value right after. So the computations of those next two parts are not too bad. If you're going to carry out the necessary computations, that's kind of vague, but the first thing you would do is get the test statistic z. It's going to be x bar minus mu naught divided by sigma, which is also divided by the square root of the sample size n. And we just happen to have all of that information ready to go. X bar was 5.0 parts per million. Mu naught on the page above, or you can also see in the null hypothesis right here, that's our mu naught value. Now, it doesn't hurt to just throw that into the notes for extra emphasis. That was 5.2. Sigma was 0.70, but let me double check that number. Yeah, 0.70. So 0.70 divide by the square root of the sample size, which was 50. All we need to do is throw that in a calculator, and we're on our way with this. So far, you could store these values in RStudio and the output Z, but this problem is not so bad just doing it a calculator way. So this would be something you would do, say, on exam 2, throw this into a calculator. 5.0 minus 5.2, divide by 0.7, divide by square root 50. Probably looks a little bit different on your calculator, but not all that different. That looks like probably a real square root symbol. When we run that, we have a negative value. It's negative because our sample mean is to the left of the hypothesized mean. But remember also, that's standard deviations. It's telling us that our data is more than 2 standard deviations away from the claim of the null hypothesis, and that is pretty far. We still need a p-value, but it looks like we're going to reject that null hypothesis in this problem. 4 decimal places is a pretty good standard value to round to for a a test statistic like Z. So I'll call this negative 2.0203. And then double check that I got those digits in. Okay, so once we have the Z test statistic, we're ready for the p-value. But it's just a really fast probability computation. We want to take a left tail test, so that's just going to be p norm of Z. So you would write here p norm negative 2.0203, and you're done. That's the entire p-value, 0.0217. So this is me doing this as, say, an exam question using a calculator. But on a real exam, I would have to give you the p-value since I'm not expecting you to have RStudio loaded up in a real exam setting. But another way you might want to do this as a homework question is just store these values and run it as one big syntax. I'll leave it up to you how you'd like to do it. But here's what the syntax would look like if we built this up a little bit more. First thing I'd probably store is the sample mean, X bar is 5.0. Next thing, probably mu naught is a good value. I'll write in as mu 0 for mu naught. It's 5.2. You need a sigma value for this procedure. So sigma would be 0.7. And you also need a sample size. In this problem, sample size n is 50. When you put all of that together in this formula, you can say Z, or maybe Z test if you want to emphasize it's the test statistic Z value. Z test would get X bar minus mu naught divide by sigma over the square root of n. And then because it's a left tail test, all you have to put in is p norm Z. So this is as a left tailed. But if it was a different problem, say a right tail test, here's what it would look like. Right tailed would be p norm Z lower dot tail equals false. If you do decide to use the syntax, keep in mind, you have to grab the right p-value to match your test. It's always matching what you have in the alternative hypothesis. And if it's two-tailed, you would go p norm, absolute value Z, lower dot tail equals false. So that's exactly how our author wrote it in. Run that whole thing, and I made a mistake. I stored it as Z test, so let me fix that. Guess that's really 3 mistakes when you think about it. Run it all again, and here's our p-values coming out. Ours was the left tail test, so that's why we picked this one here. So if you like that kind of syntax, let's share it for the sake of the notes. But keep in mind, you should be able to do it this way as well, just as an ordinary concept question on computing the test statistic from scratch. So there's the quick syntax for the entire hypothesis test, any alternative hypothesis. But now that we have the p-value, we're ready for the next most interesting phase, making the decision. It's based on alpha, so we come back here. The immediate thing I would always do after calculating the p-value is compare it against your benchmark for evidence, the significance level alpha. And this is strictly less than 0.05, which is equal to alpha. And this gives us a conclusion. This implies reject H naught. I'll say briefly. If we're rejecting H naught, that means we have significant statistical evidence the alternative hypothesis, HA, is true. So how do I know to reject? It comes back to this table. If you're less than alpha, you reject H naught. Greater than or equal to alpha is when we would fail to reject H naught. So here's what the practical conclusion is going to look like after getting through all of this work. We want to really focus on what you said right here on the planning phase. So our practical conclusion is going to be, for rejecting H naught, we have evidence that HA, right there where the red dot is, that's the truth of the population. So our conclusion would read this way. We have significant statistical evidence that, well, really we want two things in this practical conclusion. It needs to be a practical interpretation in the sense that we're not going to use any specialized language. Much like the confidence intervals, we have to get a conclusion that anyone would understand, even if they've never taken a statistics course in their entire life. And we also have to bring in the context. What is this problem all about? But if you hit both of those at once, when you just read out what mu was, what you said it was from the very beginning. I know we have to write it twice, which is kind of a tedious thing to do, but it is a requirement for the practical interpretation. So we'll get through it together. I'll be sure to always write them out twice as well, never shorting this step. We have significant statistical evidence that the true mean, or you could say average, dissolved oxygen count downstream from the plant in the interim is, we specifically said less than in our alternative, so we duplicate that language, less than. We have to mention the value that we're testing, the hypothesized value, 0.52 parts per million. So that's the entire conclusion as far as the hypothesis test goes. All we're really doing again is just rewriting what we said exactly right here. But another thing we should say before we finalize this entire problem is come back to the practical question that we indicated in the state phase. We wrote, is there significant statistical evidence this company has not reduced the pollution? That was a major thing we want to address. And once we have this statement down, we can now say, yes, low oxygen count is our way of showing they're still polluting the river at a pretty disastrous level or rate. So we can say, this shows the company, my penmanship is taking a nosedive. Let me slow down. The company, that looks like not the letter C. The company is still polluting at an unacceptable rate. And we did it, folks. That's the entire conclusion for this hypothesis test. Any last questions or comments at the moment? Okay, well, really, this is our first hypothesis test of many. We're on week 6, so we have 10 more weeks to go, and we're going to see lots more hypothesis tests, lots of things that can happen. One thing to just remind you as a kind of a big takeaway on doing this is a really important part right here because it kind of gets in our head. What is this problem all about? What is the context? If you can state the practical question well, it will probably direct you well on what the parameter mu is. Writing down mu, then the null and the alternative, this is really the hard part of both confidence intervals and hypothesis testing, where you also write the null and alternative. Once you have mu down, you'll notice the rest of it is just kind of a math problem. You get a value, you do a normal probability computation, and then when you give a conclusion, all you're doing is returning exactly back to what you said mu was in the first place. And if this was a big value, all we would have said different is we have failed to find the significant statistical evidence. So it's almost the same conclusion, whether we say we have the evidence, the small p-value, or failed to provide that evidence with a large p-value. We'll never say we have evidence that this is true. The company would love us to say that, but we can't say it in hypothesis testing. So that's the full walkthrough on hypothesis testing. There's really lots to say about it. And to end the topic, we're going to look into just a couple more statements, some concept questions like we did with confidence intervals, specifically for hypothesis testing. So first one is, we never accept the null as true in our conclusion. That's something we've been harping on a lot as we've gone through the notes, but we're going to come back to it again because it really is that important. And part B is maybe the more interesting one. The p-value is definitely not the probability the null hypothesis is true. And if that's true, the question it becomes, well, then what is the p-value in the first place? This is a major concept question, so we'll take our time with that one there. First, there's lots of ways to answer example 6 part A. Really, there's a good maxim. I forget who said this. I think it was Carl Sagan who said this. Absence of evidence is not evidence of absence. If we reframe that entire statement in terms of hypothesis testing, it goes like this. Absence of evidence that H naught is false is not evidence that H naught is true. Because if we fail to find evidence that H naught is false, does not mean it's a true statement. It just might simply mean the sample size was too slow. Or maybe just by a fluke of random sampling, we got a weird sample, a 1 in a million kind of sample, and a rare event happened. But the null hypothesis is still patently false. We have to just replicate the study maybe 3, 4, 5 times before we really see it. So absence of evidence against H naught will never count as evidence that H naught is true. And another way to think about this, if you like this circular logic analogy, you can also say, also, in hypothesis testing, we first directly and literally, let's just use directly, assume H naught is true. That means it can't be our conclusion. We were just assessing how reasonable is that statement. How strange is our test statistic in terms of standard deviations that our sample is away from a hypothesized value? Because that was the first step in hypothesis testing. It can't be our end conclusion. We're only just seeing if we can make that assumption look unreasonable based on our data. So there's lots of different takes on this. And again, if you like a court of law, that's another one to come back to. No matter what happens, we are never assuming the null hypothesis, the defendant is proven not guilty. We're just trying to see if we can prove him guilty when we assume he's not guilty and see what the evidence looks like. Well, any questions at all, folks, about this idea here? Okay, here's the next trickiest idea. When we say the p-value is not the probability that h naught is true, what is the correct interpretation of the p-value? What we're providing is a probabilistic interpretation. I want to write this down just to mention that this is not the same. I'll just write not equals the practical interpretation. So whenever we do a hypothesis test, pretty much the last step is going to ask you to do this. Provide a practical interpretation using the context. A statement that anyone's going to understand because there's no specialized language, there's no p-value, there's no mu less than 5.22 mu naught value, just ordinary language. The practical interpretation here is not the same as interpreting the p-value. That's a whole nother thing. So let's write down carefully and exactly what that means, what the interpretation would be of this p-value. So first we take a random sample, compute x bar, and z equals x bar minus mu naught divided by sigma over the square root of n. So we start by doing that. You know, it might flow better if we say what the test is as well. To test, let's write in h naught, mu equals some value mu naught. I'll say versus vs ha, mu is not equal to mu naught. I'll leave off alpha since we're mainly focusing on the p-value element, less on making a decision. So this is how we start. Then we calculate the p-value. I wrote down the two-tailed test because it's the default one. This would be the probability that z is bigger than the absolute value of z, or we wrote that in as a p-norm statement in the chart above on the notes, where z is distributed as n01. So that's where our p-value comes from. Now that we have all that on paper, here's what the actual probability interpretation is for the p-value. The p-value is the probability of obtaining a sample mean. By sample mean, we mean that x bar right there as extreme as the x bar in our study. That's not quite it, because if I try to do probability z equals the test statistic z in absolute value, that's probability 0. There has to be a range, right? So we say this extra statement, as extreme as the sample mean in our study, or more extreme. That's what every p-value is going to compute. As extreme as your test statistic, which came from that sample mean, or more extreme is encapsulated right here. Under the assumption, there's an extra assumption here, meaning this is a really complicated conditional probability. Not the kind of conditional probability you'd see in ordinary probability class. It's on a condition you made a big assumption about the population itself. It's under the assumption that the null hypothesis is true. Under the assumption that h naught, mu equals mu naught, is, just to emphasize, let's say exactly True. So it's quite a statement. It's just saying, how likely are you going to get your sample mean that you got, as extreme as that is, or even more extreme? We put in a whole range there with our test statistic when this was assumed to be the truth of the population. If that probability is really, really small, that could mean a rare event happened, or more likely, the assumption of the null hypothesis was ridiculous. It's not compatible with our sample at all. And that's why the p-value was so tiny. And that's why we would have rejected the null hypothesis for a very, very small p-value. So it takes a lot of words to actually put that down all down on paper, but it's good to see it exactly once so we can compare the difference between what the p-value is, why we never accept the null hypothesis as true. The major thing we'll do often in the homework is really this, giving the practical interpretation once we conclude our statistical study, comparing the p-value against the significance level alpha. Well, any last questions at all, folks, on getting through that last part B here? Okay, we're nearly out of time, but I want to show you what we're going to get into when we come back next week. Chapter 13 was tough because it was abstract, right? We're talking about sampling distributions, central limit theorem came into the mix. In my opinion, chapter 15 is tougher. Not because of the first part, coming up with margins of errors, deciding the sample size you need to estimate a parameter with a specific margin of error. That's not too bad. That's like the fun part of the notes. But hypothesis testing gets kind of messy. We're going to look into a little bit more about the significance level alpha as it relates to effect size, talk about the power of a hypothesis test. Then we'll look into what happens when we make a conclusion, like with that polluting company in the internal system. We could have made a mistake. We could have made a type 1 error or a type 2 error. There's a big two-way table with a specific alternative. And there's lots that goes on with this. This is very, very context heavy. So any pre-reading you can do in chapter 15 will help enormously. When we do this, if you see this for the very first time on Monday, it's a tough lesson to get through. But you know, it'll be recorded. You'll have the chance to read the book later on. So again, my call out to this section is, it's one of those sections that we'll get through. We'll see how it goes. There's a large simulation there. And we'll see how it reflects on a problem that's going to be very similar to the homework exercise as well. But we'll get through it together after chapter 15. Return to chapter 17, where the major goal is make all those conditions more reasonable, more actually applicable to the real world. So one more chapter to get through, and then we're going to just pick up statistical method after statistical method, starting in chapter 17. Well, any last questions or comments at all, folks, before we call it a day? Okay, well, have a great afternoon, folks. We'll be back to it next Monday. We'll finally be having full ordinary weeks for the rest of the semester, but have a good afternoon.
Hello, I had a question on assignment 5, exercise 1.
You bet. Let me pull that up.
Thank you.
Someone's good to get started on that one sooner than later.